deliver my greetings to all the audience, students from diverse countries, and also my supervisor, Professor Pekka Taskinen from Aalto University, and my former colleague, Dr. Ima, and the other colleagues. You are welcome to join this 2 hours course. And as Ima mentioned, I have some 2 years experience in Aalto. And today I'm going to talk after I'm going to give examples of thermodynamic application in industrial. And myself is working in Central South University now. And today I'm going to talk in 3 parts. The first one, may some of you familiar with Central South University or School of Metallurgy and Environment, but I do think that majority of you are introduction. Second is about examples, and I have picked 4 examples from multiple choices. And first one is recovery of copper. Actually, copper is just an example. There are a lot of precious metals. Recovery of copper and some other metals from smelting slag. And I am emphasizing from primary copper smelting slag. And the second example is going to be the foaming process of zinc and lead bearing materials. And as Pekka mentioned in the first and second courses, recycling and circular economy or sustainable is something we should emphasize. And the foaming process is really good in treating some zinc and lead bearing materials. And the third one is going to be the application of lead and copper binary system. And I have examples. First one, the binary system used in the lead refining process. And the second one is some work in our lab, and we are promoting it in industry, and pilot experiments are going on. We are using this binary system to remove arsenic from copper. So this is a problem in the industry now. And last one is a hydrogen example, metal recovery from acidic solutions. And you will see we are trying to substitute zinc powder with iron powder, and it's very economic, and we are making some difference with this innovation. And the last part is going to be the discussion and question part. And I'm looking forward to hear from you and looking forward to share some information with you. Okay, first of all, the introduction of Central South University. And this is a city. In your screen, in the up section, you can find the bird view of city Changsha. And this is east
very nice.
Thank
Beautiful.
you very much. And this is east part, half of the city. And this is a big river called Xiang River, actually one of the biggest in China. And this is the island. You may know a person who helped us in making the new country, the chairman Mao Zedong, and he was living and studying on this island for a couple of years. And this is a city park. And this is the east direction, and this is the west direction. I do think Indonesia is somewhere here. And our campus is located on the west side. And in the below section, you can find the campus picture. And this is a building. Sorry, so I miss it to going back. So what does it mean? Are you hearing me, Ima? Hello? Are we good? Are we good?
Yes, very good. I can hear your voice very clearly.
Okay, I found some text information. Okay, if there is any problem, try to stop me and remind me, please. Okay, in the lower section, this is a picture of our campus. Actually, we have 7 campuses in this city. So the 7 campuses located in different parts of the city. And this is the main campus. This is the teaching buildings. And this is the main library. And this is a hall, meeting hall. And actually, Central South and all of us are welcoming all of you to visit us when we have the possibility. And Central South University is founded in April 2000. by emerging 3 universities. And as you can see from my slide, the total students in our university is around 60,000 students, and half of them are undergraduate students, and we have 23,000 graduate students, including master and doctor students, and we have around 2,000 overseas students, and around, I think, 40 students from Indonesia. And we have around 6,000 faculty members, and I am one of them. The history of our university can date back to 1903. And how about the disciplines, or how about the level of our universities? You can find one number here, 1,237. Actually, this is the total number of universities in the mainland of China. So we have more than 1,000 universities. So Central South is more or less around 20, at the 20s, ranked at 20s among these 1,000 universities. And there are some national projects which are helping us in getting better conditions, learning conditions. And we have 10 disciplines which are leading in the world or in our country. And I am studying and teaching metallurgy. And this is one of the 10 top disciplines in our university. And besides metallurgy engineering, minor engineering, and nursing, and mathematics, material science engineering, and mechanical engineering, and also transportation, civil, information technology, and clinical medicine, they are also quite good. So if you are interested, you have to browse our website. An international corporation, and we are cooperating with more than 200 universities and institutions from over 30 countries. And we are having international lectures by 1,000 visiting scholars. And 3 overseas experts from our university won the Friendship Award from the central government. So this is probably the highest award in this field. And also there is one international research center with Autotech. So all mathematical people should know this company, which is leading in the technology and equipment supply in metallurgy or in mining engineering. So this is the information about Central South University. And we do think that there will be some more nice with Indonesia. How about the projects? And here's one picture. And I do think some of the students who are listening to me are in this picture. And this is, I think this is the professor from CMMAI who is helping us in this project. And there are 2 vice presidents from Central South. These 2 vice presidents from Central South who are also supporting this project. And we have 22 Indonesia students who are working with us now. And I hope you are fine now in Indonesia. And we are trying to keep our project and date, and let's exchange emails. And about degree projects, we have bachelor, master, and doctor. And you can check with this slide. And also my slides will be shared with this course, and you can try to check with this. And this special project is something I am talking now. And another doctor degree, double degree project with our university. Actually, this is my doctor's thesis, which is supervised by Professor Pikataskinen, who is also listening to us now. And this is a contract between 2 universities. This is Arto, and this is Central South University. This is a thesis written in English, and this is written in Mandarin, in Chinese. And I have 2 degrees from 2 universities. I do hope this kind of trying or innovations can happen in the future on your cases. And the last one, we can have exchange projects. So if you are interested, or if we are interested, we can have further discussion, or you can try to talk with me or try to browse the website. So this is about the CSU. And now I'm talking about something about SME. S stands for School of Metallurgy and Environment. So the history of our school can trace back to the Department of Non-Ferrous Metallurgy of Central South Institute of Mining and Metallurgy, established at 1952. Actually, this is only 3 years after the foundation of our People's Republic. So this is a national decision that we should develop our non-ferrous metallurgy, and this is a former discipline of our school. And the 1,900 students, 1,000 undergraduate, 570 master, and 278 doctorate candidates. And we have 157 faculty members. For professors, 74, and associate 54, and we have some teaching assistants. And we have 6 teaching and research buildings, and in total we have more than 30,000 square meters. Actually, we are quite rich with physical space nowadays. And we are also equipped with one advanced analytical center, and it's updating all the time. And we hope that this can support us in having better teaching and research. This is a photo family picture of our school, and this is the dean of our school, who is a member of Chinese Academy of Engineering nowadays. And all the teachers or all the faculty members are trying to sing for the party and sing for our country. This is a new building which is under construction, and we are improving the teaching and research facilities. How about our teaching and research nowadays? Actually, we have 3 majors, 3 undergraduate majors: metallurgical engineering, new energy and device materials, and environmental engineering. We have 3 majors, and 240 bachelor degrees, 140 master, and 70 doctorate degrees are granted every year. And annually, we are publishing 450 ESI papers, 300 authorized patents, and we are winning 100 million funds, project funds, which can support the research. And we have won 18 national awards, and 3 patents were industrialized, and every single of it were sold more than 100 million RMB. So this is how we are doing our research, and we are doing the papers, and we are trying to get some patents. And we are industrialized our patents, because metallurgical is an engineering, so we should get closer to the industry. And majors in our school for graduate students: and physical chemistry of metallurgy, ferrous metallurgy, non-ferrous metallurgy, environment engineering of metallurgy, new energy materials and devices, and the materials metallurgy. Actually, I am in this discipline, non-ferrous metallurgy. And this is a work done by one of my colleagues, so Professor Dai Shi. And actually the gentleman, I think the master candidate, Mr. Chen Min, who is working as a doctor candidate in art nowadays. And this is a study on the phase transition of the smelting of germicide. So this is antimony and lead smelting. So this new technology. This is the front page of JOM journal. So this is something I want to talk. And I am ending up with this picture and with this subject, non-ferrous metallurgy and JOM. So we are cutting into the second part. So we are in the examples of industrial applications. So hello? So the examples. So first of all, I'm going to talk with the recovery of copper from smelting slag, actually primary copper. Probably in Pekka's presentation, he has introduced something about primary copper and secondary copper. And I assumed that you have the background from metallurgy, from chemical, secondary copper. And I emphasize copper is just one of the valuable metals in this slag. So what is the background? So this is a flow sheet of copper making. And you know that more than 80% of the copper in the world was produced through pyrometallurgy. And the copper metal smelting, converting, fire refining, and electrical refining is a dominant technology. Hello, shall we block the noise? Yes, good. And when we are producing our primary copper, so 1 ton primary copper, so we are producing 2.2 to 3 tons of smelting slag. And you know we are producing around 20 million tons of copper per year now. So if you have the calculation right now, so there are around 30 to 50 million tons of smelting slag. So this is where we are doing. So this is the mat, so which has enriched almost all the copper, but some of them are losing here. So this is one of the newest report which has told us copper content in the smelting slag. You can see the copper in the smelting slag range from 0.6% to 1.7%. So you can follow my mouse. So the cutoff grade of copper ore in China is 0.2%. So all those numbers are much larger than the cutoff grade of copper ore. So it's something we should deal with, and we should recover the copper and other valuable metals from this material. So this is the target material. And also, along with the increasing from 2016 and 2019, those numbers are increasing. Because during the past 5 years, we are trying to increase met grade. So we are producing 74% of copper met grade in the smelting stage. So which will lead more copper loose in the smelting slag. So this is the brief background. So the production of smelting slag and is some resource. It contains a lot of copper, and also it contains some other metals. Actually, 3 years ago, one smelter in China consulted me. They are losing 6 to 10 grams silver in the smelting slag per ton. So they are losing a lot of silver simultaneously with the copper. So once we can get this copper recovery rate, we can also recover other valuable metals. So this is a very famous phase diagram. So the copper, iron, sulfur, silicon. This diagram over here, and matte somewhere here, and the smelting slag. So we can check from here. We are producing the matte, and also and the slag will contain some iron oxide. More challenges are occurring in the smelting stage, especially when we are trying to increase met grade in this stage from this star to this star. So more challenges are, first of all, the depletion of high quality copper mineral resources. And the copper content and the sulfur content in the copper concentrate are decreasing all the time. And the qualities are decreasing. So secondary materials and low quality copper concentrate are used nowadays. So when we are using low quality copper concentrate, larger amount of smelting slag will be produced. And assignment, so more impurities should be removed, more gangue should be removed, and we are producing larger amount of smelting slag. And last part, so we are emphasizing economic, but also the environmental indicators are getting strengthened and strengthened. So we should control the metal loss. We should also try to find new solutions for the smelting slag. So this is all the background. So what's the key issues? We know the background and have the target, the copper, the silver, the nickel, the cobalt from the copper smelting slag. And we have a target. So what about the key issues? And I have summarized, and also you can read this from the textbook. The occurrence of copper in the smelting slag is a critical part. How copper is lost in the smelting slag? So we should figure out this firstly. So the conclusion is that copper and other valuable metals are lost chemically and physically. As you can see, this is an industrial sample. It was actually quite the slag tapping process. Get it by fast quenching with water. Slag, you can find the major component here, particles. So this is the metal using 7% copper. So this is called lost physically. And also this is violet slag. In the smelting slag, all the in the world are using violet slag system. So it's iron, silica, and a small amount of. And here, if we are using EDS, we can find here. So copper is also lost here. So in this violet slag, or in this glassy slag, so copper is chemically lost or chemically dissolved in this violet slag. And last part, besides this matte droplets, there are some lead and copper matte. So this is the property of this sulfide. So this is a minor part, and the major part is this one. So this is physically lost, and this part is chemically lost. So this is the occurrence of copper in a smelting slag. So we have the target lost. And now the problem is that how we can get it back. So the conclusion or the key issue is that we should make the phase transition. And the copper in this violet slag, so it's chemically dissolved. So if you want to get this back, so you have to make phase transition. Otherwise, you have to lynch out. You have to lynch this violet slag with great efforts. And this is not economically, and this is not durable. So phase transition for the chemical part, and also the connection of valuable metals. So either it was physically lost or chemically lost. We should have a V in connecting those. So by settling to those matte droplets, settle down and forming a layer below the slag part, or the phase transition of the oxidic copper, and also transfer into metallic copper sulfide, and it can also grow bigger and form a layer. And only in this kind of way we can get it back. So phase transition and connection is a key issue in getting it back. And thermodynamic foundation, because the assignment got from Imam is thermodynamic application examples. So you can find why copper is lost physically and chemically. And this is one of the newest paper published by Arubis. So it's summarized the copper content in the slag. So let's contain both physical copper and chemical copper. And this is copper matte grade. So we can find out that. So it's more or less in a 9 relationship and increase dramatically after 75 weight percentage of copper in the matte. And this is the information we can get that. So it cannot be avoided. So copper will lost in this part. And also another thermodynamic information you can find from literature is the passing coefficient. partitioning coefficient. Now, this partitioning coefficient is calculated by the weight of the copper content in the copper and also the copper content in the slag. So this result is used in describing the copper distribution or partitioning coefficient. We can find out that along with increasing of copper matte, so this partitioning coefficient decreased. So the planned data, so phase actually is the calculated one very well. And the 9b represents a partitioning coefficient with 30% entrainment. Actually, the entrainment is physical matte droplets, and the other part are from oxidic. So thermodynamically, we know that when we are increasing the copper matte grade, we are oxidizing more iron into the slag. So the oxygen pass pressure of the slag is increasing. So which will driving the copper into oxidic form in the slag. But this is the main flow sheet, and we can have some other considerations. So we know copper is lost in oxidic state. So the reducing should be a promising technology in finding it. So reducing technology is good. And the second one, the copper matte can be easily separated with the slag. And copper matte is the sulfide. So sulfidation technology is another routine that we can utilize in recovering those copper. So both technology, reducing or sulfidation, both of them are working thermodynamically. And as we discussed in the previous slide, the oxygen pass pressure, in other words, the copper matte grade, as one of the key parameters in determining the copper content in the slag. And another one is the temperature. So along with the temperature, the dissolution of copper oxide in the slag will change. And by verifying the temperature, we can get phase transition of oxidic copper in the slag. And from this table, or from this picture, we can find here, so this is iron sulfide, this is lead sulfide, this is copper sulfide. And the chemically dissolved copper is oxide. So we can find at the fixed temperature, we can easily replace iron oxide with lead sulfide and iron sulfide, and it can convert to copper sulfide, and the other sulfide will convert to oxide. So this kind of replacement is also durable in making the phase transition, and it came from the sulfidation technology. So here, the sulfur to iron ratio in the slag is a critical part. And in the sulfidation technology, the particle size of the copper sulfide also determines the efficiency, because the copper sulfide can be recovered with forced flotation. If the particle is too tiny, is too small, forced flotation is not working very well with tiny particles. So those copper sulfide should be large enough. So let's draw a conclusion. Reducing technology is durable, and oxidation pressure and temperature will determine the efficiency. Sulfidation technology is another option, and the sulfur to copper ratio in the slag, temperature, and the particle size of the sulfides will determine the efficiency of this technology. And let's look at figure 1 to 6. So this is how oxygen pressure influence the smelting slag. Actually, this is a very old reference. So it's Outcombe slag. So we know that this is from a flash smelting slag. So along with the decreasing of the copper content in the slag, we can find out that we are producing copper metal, and simultaneously some other metal is also reduced, and the name is iron. All of us know that iron is a high melting point metal, So if iron is reduced, it cannot settle down. It will be a solid phase. So this will bring a new problem for us. And let's go to further. So this is a better explanation by Fexage. I think this is the work by Leuven University from Belgium. So the initial snag is from here. So if we are reducing at 1300 degrees C with carbon, and we can get the copper formation of copper, liquid copper. And once we cut into this area, we are getting the cubic crystal iron. So this is a problem. If we go further, so more iron will be reduced. So the conclusion is that by reducing technology, we are producing low copper content slag. But the problem is that we are producing iron as well. And in this part, it will bring difficulties in the practice. And another problem is that copper smelting slag always contains some arsenic. In this reducing technology, arsenic will also terminate into this metal phase. And we are producing copper, iron, and arsenic alloy. The market of this alloy is very limited. So this is a thermodynamic foundation of reducing technology. Another one is sulfidation. We are using iron sulfide or lead sulfide in replacing the oxide. And we are offering temperature or offering energy, try to get those particles grow larger enough. And we are using force of flotation in the following step. And we can clean the slag in a better efficiency. So the force flotation, the fundamental, the phase transition. So especially in targeting at copper oxide in the glassy phase. So those entrained copper matte can be easily collected by the settling. And those oxide in the glassy phase, we should transfer them. We should have phase transition. And also the particles should be larger. And this is a copper solubility in this slag system. We can find out that when we are producing very wet metals, so it's almost pure copper sulfide. And when we are verifying the iron to silica ratio, the copper loss or the oxide doesn't change. But if we are producing some lower grade copper matte, so it verifies when we are decreasing the iron to silica ratio, the oxidic or the dissolved copper in the glassy phase decreased. So this is the idea which can support that when we are using flash smelting technology, we are producing lower copper content slag after the tailing. And also the copper in the slag, we have sulfide as untrained copper matte droplets, and also the dissolved ones. And we can change with iron to silica ratio into iron silica ratio. So the solution one is, as I have mentioned, reducing can work. So how is the industrial application or industrial solution? So this is part of Mitsubishi process, so which is developed by Japanese and which is utilized, I think, is in Indonesia as well. So in the smelting furnace, they are producing high-grade copper matte, and the matte and the slag get separated in the electrical furnace. And also the slag is discarded to sell, and the copper content in the slag or in the final is larger than 0.5%. Actually, this is not acceptable by Chinese copper smelters, but those mining and metallurgy companies having very good resources, and Japan is short with land, so they are using such technologies. but this is not available in China nowadays. And solution 2 is cooling, grading, and phosphorylatation. This is commonly used in China, and I do think in elsewhere. So the smelting slag is firstly controlled cooling. So there are ladles. Around 50 tons of smelting slag are cooling within this ladle, or within 50 hours to 70 hours. And after that, they are crushing and grading with bone millings. And after that, phosphorylatation is applied. So we can find out that after slow cooling, we can find the copper matte, or copper sulfide. The copper sulfide and sulfide grow into quite a big size. So this is 100 micrometer. So this is visible, and this is acceptable, or this is durable with phosphorylatation. And the copper concentrate production, actually the cutoff particle size is 42 micrometer. So this is larger than 100. So this is why this can produce better efficiencies. And the copper in the tailings is around 0.25 percentage. And we are producing the slag concentrate, which can be fed back to the smelters. And the tailings can be used for cement preparation. And this is this is used in Japan and some countries. And this is widely used in China and some other countries. So this is the industrial solutions. And in our lab or in the south, we have some ideas. We want to do something more. The idea is that we want to co-treat the gypsum residue and the smelting slag. So the idea is that, as we have mentioned, that sulfide can be used in making the phase transition of dissolved copper in the glassy phase. So gypsum residue, it has calcium, it has sulfur. So this one can firstly transfer to calcium sulfide. So it's easily, and it can be obtained in the lab. It can also be obtained in industry. The gypsum residue, we are utilizing the sulfur, and the sulfur can be further recycled with the smelting stage. And also those valuable metals in the gypsum residue can also be recycled, or can be simultaneously recycled, especially those metals will transfer to sulfide as well in these quarry reactions. So the oxide or sulfate, they are reduced with carbon and they are forming sulfide. So the sulfide can help us in transferring copper oxide into copper sulfide. And there are a lot of energy. Around 50% of thermal energy are taken away by the smelting slag. And here we can utilize those thermal energy in making this reaction, the decomposition of calcium oxide, and also the energy can be used in helping copper sulfide in growing up. So the low oxygen pressure can be achieved, and the glassy phase will have the phase transition. And the tailings have potential utility in cement. So this is the production. So the phase transferred slag. So the oxide copper and sulfide copper will decrease because phase transition are applied. And also, besides copper sulfide, some of this oxide will be reduced by the calcium sulfide, even by the carbon. So the bare copper can also be recovered if it is big enough, and also possibly recovery of iron. So how about the thermodynamic? So we can find the calcium sulfide, it can dissolve or decompose magnetite. It can also transfer our oxide, especially copper oxide, copper oxide. So thermodynamically, it is durable and it can be achieved. The reaction, standard reaction Gibbs energy is negative. So we can run it in this temperature window. And schematic figure of this process, we can find out if gypsum and carbon is well mixed, and we are using the thermal from the smelting slag, and decomposition of gypsum happened, and calcium sulfide is produced. And those oxidic copper in the smelting slag will have the transformation, and it will transfer to copper sulfide. So does iron. And these two will aggregate and grow bigger. And when they are larger enough, they can be recycled in the phosphorylatation. So how about the result? Actually, we have tested, or we have studied different iron to silicon ratio, which representing different smelting technologies. We can easily find out that. So the sulfide formed after this technology. And if we are looking at the microstructure with BSE images, we can find out that. So very large particles, then this is 50, so this is around 100 micrometer. As I have mentioned, this can be well recycled. And also this iron can also be recycled or can be further treated. The sulfur from the gypsum can be further recycled by acid making. Some part of iron transfer into iron oxide. The iron oxide, after the crushing and bone milling, I think, or the iron oxide will transfer to magnetite, and it can be separated with magnification separation. So also have the potential of further recovery. So this is the glassy phase, which will be further sent for cement preparation. And we find out that the copper in the glassy slag is around 0.13 weight percentage. So when we are looking at a number with present technology, the lowest number is 0.25, and this number is 0.13. So around 50% of copper in the smelting slag or in the tailings can be recycled. As I have mentioned, there are around 30 to 50 million tons of copper smelting slag. So let's have a calculation. So it's a large amount of copper and large amount of very strong economic driving force. So this is an example of copper and other precious metal recovery from the smelting slag. And how about the second example? And I am going to talk about the fuming process of zinc and lead bearing materials. And lead is an important metal when you have very big iron and steel industry, because zinc is used in coating those iron from corrosion purpose, from anti-corrosion purpose. And this zinc is also produced from sulfide minerals, from hydrometallurgy. And there are a lot of zinc containing materials produced or residues produced from zinc hydrometallurgy. And those materials should be treated. And lead is another important metal, or another one of the biggest metal. I think is around 10 million tons of lead all over the world per year, and it's used mainly in batteries. And when lead is produced from sulfide minerals, and because they are twins in the minerals, in the concentrate, we are producing some zinc containing slag. And those zinc in the slag should also be recycled. And fuming is a good technology in recycling those zinc and lead. So this is some words. And as I mentioned, mentioned. So this is the flow sheet for lead making. So you can think, so oxygen, lead, sulfide concentrate, and some flags. I think Tawfiq, I think the professor in ITB, and also Jack from UQ has done a lot of work in this field, the pyrometallurgy of lead smelting. And
yes, Taufik Hidayat is my friend in here.
I think they have done a lot of work. I have published a lot of papers here. And the lead smelting practice in China is really advanced. And I try to compare the academic achievements and the industrial achievements. I do think there is a gap that we should catch up. And our academic results cannot explain some phenomena in the industry nowadays. And let's come back to the flow sheet of lead making. The lead sulfide concentrate reacted with flax, oxygen, and there are 3 stages. The first stage is oxidation smelting, and we are producing the primary lead. So lead bullion is produced here, and also a lead-rich slag, so containing more than 50% lead here. And this lead is further recovered by reducing smelting. So we are getting second lead bullion. And in this part, another slag containing, as you can see, this is a target material in my second example. So this is a zinc-rich slag or low lead slag. And we are treating them with fuming. So this is the fuming process. So in lead smelting nowadays, there are 3 stages. And also, all those stages are connected with melting phases. So hot lead-rich slag were tapped out and introduced into the reduction furnace. And the hot slag is introduced into the fuming furnace. So everything is continuous. And the environmental problems has been solved. And we are working in a very good condition nowadays. And the various technologies can be used, or various furnaces can finalize those assignments. The chief site, the bottom blowing, TSL, Vannikov. So all those technologies can be found in China. So this is why I'm talking a gap between academia and industry nowadays. The zinc-rich slag, so we can find the table 221, and this 2 tables. One is from Jack from UQ, and some information about the smelters all over the world, from Roskar, from Sweden, from ANSA, from Korea, from Trio, from Canada, from Podvegmi, from Italy, I think. So those smelters, their zinc-rich slag, we can find it contains around 5 to 18% of zinc, and it was in a melting slag. So we should recycle those zinc. And this is oxygen side blowing furnace. Oxygen side blowing furnace, which is widely used in China nowadays. So we are producing also around 15% of zinc in the slag. So all those zinc should be recycled. So does the lead here. So there's still some lead remaining after the first oxidation recovery and second reducing recovery. There's still some lead remaining in the zinc-rich slag. So we should recycle them in the fuming stage. So this is from the lead making process, and also other zinc and lead bearing materials should be co-treated. For example, I have already mentioned from zinc hydrometallurgy, the lynching residue, the iron precipitation, and also the gypsum residue. So all those materials contain some sulfur contain lead and zinc, even contain some silver and copper. They can be nicely recycled with a lead process, and after that, all those materials will ended up in this zinc-rich slag. So we should pay attention to the fuming process. So the background has already been introduced, and how about the equipment? So this is a fuming furnace from Yunnan province from China, and this is the schematical structure of the fuming furnaces. So as I have mentioned, so we can take from, so this is water jacket protection. So the full furnace, you can see the furnace is fully protected with water jacket, which means that we can use this furnace at elevated temperatures. So all those materials, zinc and lead bearing materials, can be nicely processed and well recycled in this furnace. And I have highlighted with red lines, so inlet of melting, so inlet of melting. So as I have mentioned, the slag in hot form can be directly tapped into this furnace. And also we can have some cold materials from the feeding moss. So this fuming furnace can treat both hot slag and cold materials. So this is the industrial practice nowadays in China, and also DSL and Osmat can also work in this field. And we know the practice in Korea, in Ansan. So they are recycling lead, zinc, silver, India, a lot of precious metals. Very nice with TSL. So this is the background. So how about the key issues? So we know the problem or the background is important, and we should have some attention, we should have some methods in recycling. So we should efficiently fuming zinc, lead, indium, germanium, silver, coal, copper. Actually, they can be fuming, they can vaporize, or they can also be connected in other forms like species from the melting bath. So all of them are in this melting bath, all those components. And how to get them vaporized, and also technical requirements and difficulties. We should have the consideration from thermodynamically, from economically. So the previous, we know the composition of the zinc-rich slag. So somewhere here, so it's point A. So once we get those valuable metals nicely recycled with fuming furnaces, so we are approaching point B. So it's going to be again the iron, silica, and calcium. So this is a ternary slag system again. So the problem is that how we can utilize the phase equilibrium here, and what kind of thermodynamic parameters are needed for the forming process. The core reactions is that here, so we are using carbon, and we can have carbon monoxide in this system, and carbon monoxide can reduce our oxide in the molten slag very well. And firstly, we are getting zinc vapor and lead vapor. So they can escape from the melting bath, and after that, we can recycle it from the dust or from the flue gas. And this is very old figure about the reducing of iron, zinc, and lead with calcium and calcium dioxide mixture. So this is very popularly used in iron making and also in some other fields. And as we can see, so this is how we can produce iron. So at lower temperature, we can produce from hematite directly to iron. But when we are approaching to higher temperature, so we have to came across iron, ferrous oxide. And after that, ferrous oxide can be reduced with carbon monoxide, and we are getting iron. So as I have mentioned, the slag system of zinc-rich is zinc, calcium, iron, and silica. So iron is also cations. It can also also reduced. You can find out that when we have the low temperature or relatively low temperature below 1500 Kelvin. So we can find out that the ferrous ion can be reduced. And here in this area, zinc is still predominant. The predominant species of ion is still of zinc is still zinc oxide. It means that we are reducing iron instead of zinc oxide. So thermodynamically, we should know that zinc oxide and lead oxide, they are targets instead of ferrous oxide. And as I have already discussed or analyzed, so at low temperature, so below around 1300 degrees C, iron will be firstly reduced instead of zinc. And lead can be very easily reduced in these cases, or in this process window. So we know that when we cross its joint point, and the iron is still stay with oxide form. So this is the ferrous, but we are producing zinc oxide to zinc vapor. So here we have zinc vapor, and we have lead vapor, and we have ferrous oxide in the slag. So this is what we should do. And also, I have a horizontal line here. So the cross line, we are entering this part. So both iron and zinc will be metallic form. So the reducing atmosphere should be lower than this line. So we should be somewhere here. So the conclusion is that zinc oxide, lead oxide, they are targets, and high temperature is needed. And oxygen partial pressure should be carefully monitored. And actually, in industry, we are using the carbon to oxygen ratio to monitor this parameter. And we also know that because of the requirement of temperature, once our lead and zinc escape from the melting bath as metal vapor, the temperature will decrease. So very rapidly, zinc and lead vapor will be oxidized by carbon dioxide. So we can only recycle, or we can only connect zinc oxide and lead oxide in the flue dust. So this is thermodynamic foundation. So how does industrial solution? So as I have already mentioned, so we should play this game in this area. So the iron should stay as ferrous oxide, and we should have the zinc as vapor, and so does lead. So this is a place, and look at the activity, the zinc oxide activity in the slag, and also the zinc vapor pressure in the gas form. So once the zinc oxide activity is smaller than 0.1, the zinc vapor pressure is not increasing anymore. Actually, this thermodynamically told us that it's going to be very difficult in getting zinc-free slag. So there will be some zinc losing in the final slag. This is also a slag we connected from a smelter, lead smelter in China. Actually, one of the best one in China nowadays. And this is a fuming slag. As I have already mentioned, lead and zinc can be recycled. As we can see, so this is number 9. Point number 9. So we can find the magnesium, alumina, silica, calcium, iron. So they are slag components, and we are still having some percent of zinc remaining, and also some lead. So they are very nicely recycled, but there are still some lost. And averagely, this number is around 2%, and this is 0.5%. So this is acceptable. How about the others? We can find this part. So this is number 8. We can find metallic iron is reduced. And I do think this is because we are emphasizing the processing window here, but in some cases or in some sports or in some areas, there will be some place or some windows far from this area. So the ion will be reduced, especially when it was rich with carbon monoxide or with carbon. So ion can also be reduced. So this is the industrial solution and industrial result. And I think we are good with the quality. So I'm going to continue with my third example. So the application of copper and lead system. And this is actually very important one. And I try to cite the work from UQ, from Xinxian, and I think from Jack. And they are emphasizing, or they are offering the idea that these three metals should be processed in one unit or in one factory. So those streams should have been nicely organized and exchanged. The copper, lead, and zinc. And now we are talking about copper and lead binary. So this is we can find out here. So in the lead processing, and we are producing some copper-containing species, the copper matte, even copper drossels, and it can be sent to copper process. And in copper making, there will be some lead dust. It can be sent to hydrometallurgy, and the lead-containing residue will be processed with lead hydrometallurgy. And also zinc fumes. As I mentioned, they are secondary zinc oxide and lead oxide, so they can be sent to zinc hydrometallurgy. After leaching, so lead will transfer to lead sulfate, and it can be sent back to the lead. So this is very well designed and very well recycled, And the copper and lead system is a fundamental system in metallurgy, not only in these three metal making process, but also in metallurgy and also in material science, in solder, in alloy, and in a lot of other electrical industries. So this is an idea. Actually, I agree with this one, and this should be promoted all over the world. So how was the topic coming, or how was my example copper and lead binary system? So as you can see, this is crude lead, and this is refined lead. So the color is different, and also there is something we should recycle. So if we are selling the copper or the lead crude in such a form, the price is low, and the copper, the silver, and all those more expensive metals are sold with the price of lead, which is not economic. So we should recycle our copper, so does other metals. And if we are separating copper from crude lead, so we have to taking care, or we have to take the copper and lead binary system into consideration. And this is a copper anode scrap. So some of you may have the experience in a copper smelter, and on the surface they are black and they are anode slime, and after the cleaning of anode slime, they are also dark color, because which is very high with arsenic. And I have a figure here. So all over the world, the arsenic containing our copper concentrate in around 10 years ago, it's 0.15. And 5 years ago, the number grows to 0.23. When arsenic accumulates, or when arsenic grows in the concentrate, it grows everywhere in copper smelter. So when the arsenic is high in this copper anode, so we can find out that there are build-ups or noodles building up on the copper cathode. So this is not acceptable, and this is the result of floating anode slime or other problems. So this should be avoided. And when we have such cathode, we cannot use automatic machines. So it should be manually shaped, manually fixed. So it's labor demanding and economically demanding. But when we want to remove or we want to separate arsenic from this part, we know that lead is another major component on this black stuff. So the copper, lead are major and arsenic is minor. So how should we separate arsenic with the presence of copper and lead? So this is the question and we should answer. And in copper or in lead making, so this is the concentrate of galena, so lead sulfide. So there are always some copper coexist or zinc coexist. So we have two taking care of all those metals. Lead is major and zinc should be recycled with assistance with synthetic hydrometallurgy. And copper should be recycled with, should also be separated and recycled. And in the copper making flow sheet, so this is flash. Again, we have already introduced in the first example and the second time. So we know that the concentrate is where arsenic comes from. And once the arsenic comes into this system, and in flash, around 1/3 of the arsenic can terminate, can enter the slag and then leave the system with slag tailings. And the other 70% are recycling in this system. And in the smelting and converting stage, some percent of copper can be, some percent of arsenic can be removed. But in this fire refining stage of bleached copper, of fire refining of bleached copper, they cannot be well removed. Arsenic cannot be well removed. Less than 1% arsenic can be removed in the fire refining stage. So we are using this binary system from copper and lead. So first one is here and second one is here. So obviously, this is lead-rich corner, so which can be utilized in the lead refining application. And here, this is copper-rich corner. So copper-rich corner, which should be used in the fire refining. So when we want to apply this binary system into these applications, we should know the phase equilibrium. So this is the fully liquid, and there are two liquids. One is rich with iron, one is rich with lead, and the other one is rich with copper. And here is also, this is a liquid phase with one solid phase. The liquid phase is a phase consisting of lead and copper, and the solid phase is copper cubic crystal structure. And in the lower part, we have the liquid alloy, which is rich with lead, and another is copper solid. So we should have our treatment, or we should have our technology working in this area and in this area. And also, when we want to remove arsenic from the copper and lead containing system, we should know the impurity behaviors. Otherwise, we have no idea. So all of them are based on thermodynamics. And once we know thermodynamic and is durable, and we have technology, and whether we have the equipment, and whether it can be technically promoted. So this is crude copper refining process. So we are targeting in this part how to remove copper from the crude lead. Crude lead and copper, and lead is on this corner. So we are making larger magnification on this specific area. So this is a pure lead, so whose melting point is 327 degrees C. And here's the eutectic point. That's in between copper and the lead is 320 degrees C. And this eutectic point 6% of copper dissolve or will dissolve in this liquid part. So here we have the fully liquid phase, and here we have the liquid alloy, which is extremely rich with lead, and another part here we have the copper solid. Because of the difference of the density of copper and lead, so the copper doses will float onto the surface of the lead bus, and the lead will be purified at the bottom layer. So this is how it was used. How it was used thermodynamically is durable. And this is a furnace used, I think, popularly used all over the world. And here, the first one is a tire. We are supporting some energy. And this is crude lead inlet, and this is operating door. And we are using some tools try to get the slag, the copper drossets, even matte tapping. So we are tapping them out from here. And this is passing in wall. And all the refined lead entering this zone, and with the siphon, and we are tapping our refined lead with 6 and 7. So this is very well designed. And on the above side, there is a tire and also the lead at high temperature. So it's several hundred, more than 800 degrees C. And along with developing the dips of the bus, the temperature is decreasing. And in the lower layer, so the temperature is 340 degrees C, around that. And we know that the eutectic point is 326. And this is some 10 degrees higher than that in order to avoid the high viscosity of the liquid lead, and which helps the separating of copper drossels and the lead melt. And also, we know the eutectic point. At the eutectic point, the copper content in the lead is 0.06. But with the formation of some intermetallic compounds like copper arsenate or copper sulfide, it will decrease the copper content in the refined lead. So the lead is very well refined, or the copper can be very well removed and recycled with such a setup and with such a technology. And the second half of the copper and the lead binary system is arsenic removal. As I have mentioned, arsenic is a headache, is a problem in copper. And the smelting stage and converting stage are so huge, and it's very well developed. It's very difficult to make any changes or make any innovations. But the fine refining stage is relatively small, and which is the last stage of pyro units or pyro processes. So it's promising and durable in making innovations here. But arsenic is barely removed in very refined technologies. Based on our observation and investigation, less than 1% of arsenic can be removed in very refining technologies. So if you are using some special treatment, like using some sodium carbonate flags, it helps, but it brings new problems. And arsenic will accumulate in this process in the whole system. So along with the increase of arsenic content in the copper concentrate, this problem will become more huge, and the problem should be solved. So the enrichment of, when we want to remove arsenic from the very refining technology, so we should know the key issues or the critical part. So the enrichment of arsenic and the targeting removal should be critical steps. So let's look at the thermodynamic background. So let's see the binary phase diagram between arsenic and copper. So this is this highlighted area. This is where we are using the fire refining. We're doing the fire refining, especially in this region. So this is fully liquid. So copper and arsenic, even lead, are well mixed. And I have told some friends that when we have arsenic in melting copper, it's just like small fishes in the ocean. It's so difficult of catching them and separate them. So how to get those fishes is that actually in name of arsenic. Enriched and targeting removal is our work. And I have an idea that how about adding a stone on the fish will sink at the bottom of the ocean, or make a balloon on the fish, which will help the fish float on the upper layer. So which can help us in enriching the arsenic in this field. And you can see here, so in this whole range, so this is the mole ratio. So almost when we have arsenic in the copper, we cannot remove it efficiently. And this revelate, or this, tells the difficulties. And the activity coefficients of arsenic, so it's very minor. So it's minus, so there's minus 0.001 or minus 6.001. So thermodynamically, arsenic is very difficult to remove. So as I have explained, can we remove in the fourth stage? And here we are. So we are using the arsenic, lead, and copper ternary phase diagram in this technology or intelligent this application. So this is the corner, so which is very rich with copper and which stands for the fire refining process of copper. So we are making the process with two phases. One is liquid and another is copper solid. So this is an experiment carried out in our lab. So we equilibrated some alloys, so which contains 95% copper, 2% lead, 1% arsenic, 1% antimony, 1% bismuth at 150 degrees C for 2 days. We can find out that the liquid phase contains 90% of copper, but it contains around 0.8% arsenic. And in another phase, this is copper, so it's 8.6% of copper, and arsenic is only 0.1%. So we can find out that arsenic, antimony, and bismuth are very well enriched with this phase, and this has helped us in making the further treatment. And we all know that the requirement or the limitation of arsenic content in copper anode is 0.3%. So here, when we have this enrichment, the arsenic in the copper phase can fit the requirement of 0.3. And this part, because this is liquid, and we have copper here, we have lead here, and once we inject oxygen inside this system, the oxygen can be transported with copper and lead to arsenic, antimony, and bismuth. Those impurities can be very nicely removed by slagging. So this is a smelting system. So arsenic enrichment, targeting oxidation, and slag modify. So this schematic picture is arsenic bearing copper lead phase and another copper phase, which means refined copper, and a modified slag and a gas dust phase. So this is a 4-phase refining system. And in the experiment, this is the lab application. So as I have mentioned, in traditional fire refining process, less than 1% arsenic can be removable. But here in our studies, we can find out around 33% of arsenic has been removed efficiently. So 30 times larger than that of industrial numbers. So this is well designed and well tamed. And the copper recovery rate is 93. So which is comparable with the fire refining in the shaft furnace, in the rotating furnace, or in the anode furnace. So this is the result solution. The result of our lab. Okay, so first three, we are mainly from the pyro part. We are using thermodynamics based diagrams to solve problems from pyrometallurgy. And my fourth example is a hydro one, metal recovery from acidic solutions. So the background is that actually when we are making copper, lead, zinc, cobalt, nickel, we always use some water, and we always produce some solid waste. So the water will contain some metals and even some sulfate and some solids. They are toxic solids. They should be treated, and we usually with acid, lynched with acid. So all those valuable metals will report into aqueous solution. And as I have mentioned, so arsenic is a common impurity elements in our concentrates, especially in sulfide concentrates. Once we are producing metals, arsenic is liberalized. So it reports to metal, to slag, to gas, to water, as anywhere. And when we are leaching materials with acid, arsenic will report to the solution as well. So there are some economic driving force. We are recycling copper, zinc, cobalt, nickel, even some other metals. And industrially, they are using zinc powder to recover those metals by replacement from a solution. But this is not very well applied because of the formation of toxic gases. So hydrogen, arsenide. So this is toxic. One bite, I think one knife. With one bite, probably there's no medicine for that. So this is very toxic one. And also when we are using copper powder, zinc powder, so this is something expensive. And cost will limit the application. And this is a typical composition of wastewater in copper smelter in China. And we can find it contains quite a large amount of copper, lead, and arsenic content is relatively high, and also is acidic. And the solid waste in a zinc smelter contains a lot of copper. So this is around 1%, less than 1% copper, and it also has arsenic. So once it's lynched out, all those metals will reported into the aqueous solution. And zinc powder replacement should be substituted. We should find a better solution. So what is the solution? And how about use another cheap powder, iron? Iron powder is proposed to solve this problem because iron is much, much cheaper than zinc powder. But when we are using iron powder to replace zinc powder, whether we can obtain those valuable metals from the aqueous solution. So this is the first question. And the second question is that whether we are producing these toxic gases, hydrogen, arsenide, whether we are producing it as well. Can we solve this problem as well? So this is the second question. So both questions should be seriously addressed before we can